Welcome to Lesson 10 of Applied Physics. This lesson covers work and energy. The concepts of work and energy are closely tied to the concept of force because an applied force can do work on an object and cause a change in energy. Energy is defined as the ability to do work. In this lesson, you will cover the following objectives. Understand the basic terms associated with work and energy. Learn how to make an energy bar chart and use bar charts to solve problems. Define the terms work and energy. Determine the dot or scalar product of two vectors. Define the terms kinetic energy and potential energy. Identify the work-energy theorem and use it to solve problems. Define what is meant by the mechanical energy of an object. State in words the principle of conservation of mechanical energy and the principle of conservation of total energy. Solve problems involving energy conservation in a systematic way. Determine the work done on an object by a variable force. Distinguish between a conservative force and a non-conservative force and be able to state the definition for each of these types of forces. Determine analytically whether a force is conservative or non-conservative, and determine the conservative force function that corresponds to a potential energy function. The concept of work in physics is much more narrowly defined than the common use of the word. Work is done on an object when an applied force moves it through a distance. In our everyday language, work is related to expenditure of muscular effort, but this is not the case in the language of physics. A person that holds a heavy object does no physical work because the force is not moving the object through a distance. Work, according to the physics definition, is being accomplished while the heavy object is being lifted, but not while the object is stationary. Another example of the absence of work is a mass on the end of a string rotating in a horizontal circle on a frictionless surface. The centripetal force is directed toward the center of the circle and, therefore, is not moving the object through a distance. That is, the force is not in the direction of motion of the object. However, work was done to set the mass in motion. Mathematically, work is W equals F times X, where F is the applied force and X is the distance moved, that is, displacement. Work is a scalar. The SI unit for work is the joule, or J, which is Newton meter, or kilogram meters over seconds squared. If work is done by a varying force, this equation cannot be used. This figure shows the force versus displacement graph for an object that has three different successive forces acting on it. The force is increasing in segment 1, is constant in segment 2, and is decreasing in segment 3. The work performed on the object by each force is the area between the curve and the x-axis. The total work done is the total area between the curve and the x-axis. For example, in this case, the work done by the three successive forces is shown. In this example, the total work accomplished is shown here. For a gradually changing force, the work is expressed in integral form, shown here, where the integral allows you to calculate the area. Kinetic energy is the energy of an object in motion. The expression for kinetic energy can be derived from the definition for work and from kinematic relationships. Consider a force applied parallel to the surface that moves an object with constant acceleration. From the definition of work, from Newton's second law of motion, and from kinematics, we get this equation. Substitute the last expression for acceleration into the expression for work to obtain this equation. The right side of the last equation yields the definition for kinetic energy. Kinetic energy is a scalar quantity with the same units as work, joules. For example, a 2 kilogram mass moving with a speed of 3 meters per second has a kinetic energy of 9 joules. The previous derivation shows that the net work is equal to the change in kinetic energy. This relationship is called the work-energy theorem. Potential energy, also referred to as stored energy, is the ability of a system to do work due to its position or internal structure. Examples are energy stored in a pile driver at the top of its path, or energy stored in a coiled spring. Potential energy is measured in units of joules. In the figure, you see a biker who has kinetic energy as he rides up to the top of the hill. When he reaches the top, he is just barely moving, but he possesses a large amount of potential energy, which can be converted back to moving or kinetic energy as he rolls back down the hill. At the bottom of the hill, he will no longer have the potential energy, but he will have converted it to kinetic energy. Work will have to be done by something or somebody to cause the object to stop. Gravitational potential energy is energy of position. First, consider gravitational potential energy near the surface of the Earth, where the acceleration due to gravity is approximately constant. In this case, an object's gravitational potential energy with respect to some reference level is PE equals mgh, where h is the vertical distance above the reference level. To lift an object slowly, a force equal to its weight, or mg, is applied through a height, or h. The work accomplished is equal to the change in potential energy shown in this equation, where the subscripts F and O refer to the final and original heights of the body. Launching a rocket into space requires work to separate the mass of the Earth and the rocket to overcome the gravitational force. For large distances from the center of the Earth, the equation is inadequate because g is not constant. The general form of gravitational potential energy is shown here, where capital M and lowercase m refer to the masses of the two bodies being separated, and lowercase r is the distance between the centers of the masses. The negative sign is a result of selecting the zero reference at lowercase r equal to infinity, that is, at very large separation. Elastic potential energy is energy stored in a spring. The magnitude of the force required to stretch a spring is given by capital F equals negative k times x, where x is the distance of stretch, or compression, of a spring from the unstressed position, and k is the spring constant. The spring constant is a measure of the stiffness of the spring, which stiffer springs have larger k values. The potential energy stored in a spring is given by PE equals 1/2 kx squared. Change in potential energy is equal to work. The gravitational force and the force to stretch a spring are varying forces. Therefore, the potential energy equations given can also be derived from the integral form of work shown here. Power is the rate of doing work. Average capital P equals capital W over T, where T is the time interval during which work is accomplished. Another form of power is found from W equals F delta X, and substitution of average velocity of the object during time for the following. The principle of conservation of energy is one of the most far-reaching general laws of physics. It states that energy is neither created nor destroyed, but can only be transformed from one form to another in an isolated system. Because the total energy of the system always remains constant, the law of conservation of energy is a useful tool for analyzing a physical situation where energy is changing form. Imagine a swinging pendulum with negligible frictional forces. At the top of its rise, all the energy is gravitational potential energy due to height above the stationary position. At the bottom of the swing, all the energy has been transformed into kinetic energy of motion. The total energy is the sum of the kinetic and potential energies. It maintains the same value throughout the back and forth motion of a swing. Review the equations for each of the points on the pendulum. Note at point C, the potential energy is dependent upon the height, and the rest of the total energy is kinetic energy. This image shows you the fundamentals of power generation via a water flow spillway turbine system. This is an example of generating power from the potential energy stored behind a dam. Something, probably water, needs to be available with an energy potential to cause the rotation of the turbine blades. When the turbine blades are forced to spin, then a rotor can also be made to turn, and a generator can produce electrical power from the transference of energy in an amount of time via this process. One tool which can be utilized to express an understanding of the work-energy theorem is a bar chart. A work-energy bar chart represents the amount of energy possessed by an object by means of a vertical bar. The length of the bar is representative of the amount of energy present, with a longer bar representing a greater amount of energy. In a work-energy bar chart, a bar is constructed for each form of energy. Consistent with the work-energy relationship discussed in your textbook, the sum of all forms of initial energy plus the work done on the object by external forces equals the sum of all forms of final energy. We will investigate the use and meaning of work-energy bar charts and make an effort to apply this understanding to a variety of motions involving energy changes or energy transformations. In a work-energy bar chart, a bar is used to represent the amount of each term in the initially displayed equation. Consequently, the sum of the bar heights for the initial condition, initial energy plus external work, must equal the sum of the bar heights for the final condition, final energy. Since the potential energy comes in two forms, the elastic potential energy stored in springs, PE_spring, and the gravitational potential energy, PE_grav, the previous equation is rewritten as shown. The following procedure might be useful for constructing work-energy bar charts. Consider a ball falling from the top of a pillar to the ground below. Ignore air resistance. The initial state is the ball at rest on top of the pillar, and the final state is the ball just prior to striking the ground. Given this motion and the identification of the initial and final state of the ball, decisions can be made about the presence and absence of each form of energy. Since there is no motion at the top of the pillar, there is no initial kinetic energy. Since the ball is elevated above the ground while on top of the pillar, there is an initial gravitational potential energy. There are no springs involved. Thus, there is neither initial nor final elastic potential energy. In the final condition, just prior to striking the ground, the ball is moving. Thus, there is a final kinetic energy. And finally, the ball is no longer elevated above the ground, so there is no final gravitational potential energy. The ball falls under the influence of gravity alone. Thus, there are no external forces present nor doing work. The diagram summarizes this analysis. Observe that this work-energy bar chart reveals that there is no kinetic and elastic potential energy in the initial state. There is no gravitational and elastic potential energy in the final state. There is no work done by external forces. The sum of the heights on the right, 5 units, equals the sum of the heights on the left, 5 units. It is not important as to how high the two bars are in the bar chart. If the bars were 4 units high instead of 5 units high, then it would be an equally acceptable bar chart. The decision about bar height is entirely arbitrary. It is only important that the sum of the bar heights on the left balance the sum of the bar heights on the right.